Welcome to our deep dive into the world of register transfer. In digital systems, register transfer is a fundamental concept that describes how data moves between registers within a computer or digital device. Understanding register transfer is crucial for anyone interested in computer architecture or digital design. In this video, we'll break down the basic concepts, explore different types, and see how register transfers play a vital role in the operation of modern computers. Let's start by understanding what a register is and why transferring data between them is so important. A register is a small, fast storage location within a computer's processor. Registers temporarily hold data instructions or addresses that the CPU needs to access quickly. Unlike main memory, registers are directly accessible by the processor, making them essential for efficient computation. Registers come in various types, such as general purpose, special purpose, and status registers. Each serves a unique function in the execution of instructions. Now that we know what registers are, let's see how data moves between them. Register transfer refers to the process of moving data from one register to another within a digital system. This transfer is typically controlled by signals and is fundamental to the execution of instructions. Register transfers can involve simple data movement or more complex operations, such as arithmetic or logical manipulations. The ability to transfer data efficiently between registers is what enables a processor to perform tasks rapidly and accurately. To describe register transfers, we use a special notation. For example, the statement R2 left arrow R1 means that the contents of register R1 are transferred to register R2. This notation is concise and helps designers and engineers specify the exact operations that need to occur during each clock cycle. Understanding this notation is key to reading and writing register transfer level (RTL) descriptions. Register transfers are managed by control signals. These signals determine when and how data moves between registers. For instance, a control signal might enable a register to load new data or trigger a transfer at a specific clock edge. Control logic ensures that data is transferred only when required, preventing errors and ensuring synchronization within the system. Register transfers can be synchronous or asynchronous. Synchronous transfers occur in step with a clock signal, ensuring all operations are coordinated. Asynchronous transfers, on the other hand, happen independently of the clock, triggered by specific events or conditions. Most modern processors use synchronous transfers for reliability and predictability, but asynchronous transfers are useful in certain specialized applications. Another way to classify register transfers is by how data is moved, parallel or serial. In parallel transfer, all bits of data are moved simultaneously, making it fast but requiring more hardware. In serial transfer, data is moved one bit at a time, which is slower but uses fewer connections. The choice between parallel and serial depends on the application's speed and hardware constraints. Let's look at a simple example. Suppose we have two registers, R1 and R2. If we want to copy the value from R1 to R2, we use the notation R2 left arrow R1. This operation is controlled by a signal that enables R2 to load the data from R1 at the right moment. Such basic transfers are the building blocks of more complex operations in digital systems. Sometimes, register transfers occur only if certain conditions are met. For example, a transfer might happen only if a status flag is set. This is called a conditional register transfer. The condition is checked by the control logic, and only when it's true does the transfer take place. This mechanism allows for more flexible and efficient data handling. In many systems, registers are connected via a common bus. A bus is a set of shared lines that allow multiple registers to communicate efficiently. Bus-based transfers reduce the number of physical connections needed and simplify the design. Control signals select which register can place data on the bus and which one can receive it, ensuring orderly data movement. A multiplexer, or MUX, is often used in register transfer systems to select which data source is connected to a register. By using control signals, a MUX can route data from one of several registers to a destination register. This adds flexibility and allows for more complex data paths within the system. Register transfers aren't limited to just moving data. They can also involve arithmetic operations. For example, a register might receive the sum of two other registers, R3 left arrow R1 plus R2. The arithmetic logic unit, ALU, performs the calculation and the result is stored in the destination register. This is a core operation in all processors. Similar to arithmetic operations, register transfers can also involve logical operations like AND, or not. For instance, R4 left arrow R1 and R2 means the result of a logical AND between R1 and R2 is stored in R4. These operations are essential for decision-making and control flow in digital systems. Shift operations are another type of register transfer. In a shift operation, the bits in a register are moved left or right, often with new bits shifted in from one end. For example, a left shift operation on R5 moves all bits one position to the left, which is useful for multiplication by 2 in binary arithmetic. Register transfer level, or RTL, is a design abstraction used to describe the flow of data between registers and the operations performed on that data. RTL is widely used in hardware description languages like VHDL and Verilog. It allows designers to model and simulate digital systems before building the actual hardware. Timing is critical in register transfers. The clock signal coordinates when data is moved, ensuring that all parts of the system operate in harmony. Setup and hold times must be respected to avoid errors. Proper timing analysis is essential for reliable digital design. In CPUs, register transfers are at the heart of instruction execution. Every instruction, from simple data movement to complex arithmetic, involves transferring data between registers. The control unit orchestrates these transfers, ensuring each step of the instruction cycle is executed correctly. Microcontrollers use register transfers for both computation and control of peripherals. For example, writing to a control register can turn on an LED or start a timer. The principles of register transfer apply not just to CPUs but to all digital systems with programmable logic. Register transfers are also involved in memory operations. When data is read from or written to memory, it often passes through registers. This buffering allows the CPU to process data efficiently and coordinate with slower memory devices. Input and output operations also rely on register transfers. Data from external devices is loaded into registers before being processed, and output data is transferred from registers to the outside world. This mechanism ensures smooth communication between the CPU and peripherals. To sum up, register transfer is a foundational concept in digital systems, enabling efficient data movement and processing. Whether in CPUs, microcontrollers, or I/O operations, understanding register transfer is key to mastering computer architecture. With this knowledge, you're better equipped to design, analyze, and optimize digital systems for a wide range of applications.